Okay. So one of the problems that we're getting to is we're talking about confidence intervals for for mean for means t, and we talked about yesterday what's the difference between mu and theta and x bar and s at x, and then how likely is it that you want to find mu, but that you don't know the population or standard deviation? So we talked about that a little bit. There is a problem that talks about a guy working at Guinness Brewery who developed something that was not accepted, so he went in and submitted it as a student. And so it really talks about if not normal kind of squish situations, students' t-distribution, if we use t-scores instead of z-scores. Okay, remember z-score is just another way of saying how far we are from the average. It's a standard deviation, but has decimals in there and stuff. Or I guess you could have fractions if you want to. And then t-scores are calculated by the formula that's given there, which becomes you have a fraction over a radical. And then there's the standard error, which is s over the square root of n. And then it talks about degrees of freedom. Okay? So this is just another way to use a table. So degrees of freedom is normally always one less than your actual data that you've gathered. Okay? And then it talks about the next page says t interval for one mean. That's going to be the same type of equation that we've used, except they're trading out t and z for t. Yes. And then things that take place with this is you have a standard random sample, 10%. Theta is not known, and n is greater than 30, or the population is normal. So that's not going to come in a huge mean right now. But let's talk about the damn road. So the damn road, they gave us this data, and this was just observed speeds that took place over a certain amount of time on the damn road. And so you guys all see the table? Okay. So what I want to do with that, let's open the calculator, is once they give you this data, you're going to have to do the one variable statistics for it. Okay? So you're going to have to find the mean. And then remember there's two different standard deviations that we're going to use. Now we're going to start using the other standard deviation. So I'm just going to plug in this data into the calculator. Okay. So stat, edit. Holy crow, there's a lot of information here. I don't want any of this. What did I do? Somebody keep an eye on this, make sure I'm doing these numbers right. I'm going across. I'm plugging in the example 1 on the second page of 7.2. All right, so I should have 32 pieces of data, which I do. You know that when you look at number 49, it says L1 in parentheses 32. That means there's 32 pieces of data that plugged in. It's a 4x8 grid or an 8x4 grid, however you want to look at it. Which means there's 32 things. So if there's 32 numbers, and I said just a couple seconds ago, or a couple minutes ago, degrees of freedom are always one less than our number. So if there's 32 pieces of data, what's my degrees of freedom? 31, right? That should be pretty simple. Okay? So from here, I'm just going to go stat, calculate. I'm going to do the one variable statistics of my list 1. Hit enter, and then I get this information. So it tells me I have an average of 45.40 or 45.41 roughly. The summation of all my data is 1453. If I square all my data and sum it up, I get 66917. And then I have the 2 standard deviations. Okay? Where's my number off there? Oh, there it is. Okay. So, being we're using a sample, that's our sample standard deviation. So I'm going to use 5.4. Wait. Time. 5. So I have a sample. Remember I said these are backwards. This is the one I want to use, 5.42. Okay, so think of your, and I don't know why I did it, but think of your sample. Go to the other standard deviation, which you'll be using the n-1 for your degrees of freedom. So that's what the information you have. It says, do people speed on the damn road? Yes, but maybe not. And you know the one that doesn't speed because they have a line of cars behind them. That's not the problem, but I was just speaking from experience. Random sample of 32 cars is found. The data listed on the table. Construct a 95% confidence interval for the average speed on the damn road. Okay, so that's all the information I need from the calculator. I'm going to just go to the board. So I have 32 pieces of data. I have an average speed of 45.41, rounded to 2 decimal places. And then I have a standard deviation of 5.42. Okay? So now we need to create, using this equation, we're going to use this equation. Well, things I know, this looks like the same equation we have been using, but I need to fill in a t versus a z-score. So I'll get to that in a moment. So I have E is equal to, my sample, or my S is 5.42. The number of items I'm looking at is 32. So then I have to figure out what T is. Let me erase that. Okay? This is where we're going to find T. Degrees of freedom, how much? 31. What is my confidence interval that I'm trying to create? 95. So if I'm trying to create a 95% confidence interval, if I have the area between here being 95, the 2 tails account for how much percent? The 2 tails here and here account for how much percent? 5%. So each tail is going to account for how much percent? 2.5%. And 2.5% as a true decimal is what? 0.012.025. Okay, so I'm going to use degrees of freedom this, 95% confidence interval, and 0.25. Okay, so we're going to go to the table in the back. It's going to be table D for the T distributions. So what I'm going to do is my degrees of freedom are the left column, so it says DF. You're going to go down to where you get to 31. What do you notice? No, there's not a 31. So let's go to the 30. That's the next closest number to it. Is that okay? Okay, so at 30, I'm going to go and I'm going to find the 95%, which means my tail is going to be 0.025. So at 30, I'm going over to 0.025, and that looks like 2.042. Did I do that right? So I'm going to plug 2.402 into here. What's that? Say it one more time. Oh, there's. Oh, that's right. I'm sorry. 2.0. Oh my goodness, dyslexia is working well for me. Thank you. All right, doing that math, that's going to be the value that we will add and subtract from the average or the mean. Okay, so using the calculator, I'll reduce it down. I'm going to go 2.042, that's right, times 5.42 divided by square root of 32. Enter. So 1.96. Is that okay? So now I'm going to go, for my confidence interval, I'm going to go 45.41 minus 1.96 and 45.41 plus 1.96. Somebody do that real quick for me. 43 point something. Anybody with a calculator? So 45.41 minus 1.96. $43.45. And then 47.37. 47 point what? 37. Okay. So let's get the terminology down. What confidence interval did we set this at? 95. So I'm going to see if I get the lingo right for you guys. If I were to duplicate the same test, collecting data the same way, the same road conditions at the same time on the road, collect my data, I am 95% confident that my mean of my newly collected data will fall between 43.45 and 47.37. So could the mean be a moving target? Yeah. If I'm 95% confident that if I collected my data using the exact same method, during the exact same time, exact same day, exact same road conditions, temperature, everything out there, I'm not going to change in too many things. I'm trying to keep everything as consistent as possible. If I'm still going to select 32 pieces of data of cars, I am 95% confident that my new average is going to fall between those two averages. Or my new mean falls between that confidence interval. Does that make sense? Here's where statistics really starts leaving people, because all of a sudden you start putting more and more percents and numbers into the problem that people want to start saying, oh, I'm going to multiply everything by 0.95. This is 95% confidence. No, all you're saying is you are pretty doggone confident because it was done randomly the first time. If you do it again randomly, with everything pretty much being the same, you're 95% confident that your new mean of data that you do falls between those two. Could it fall outside? Yes, there's a 5% chance that it falls outside. Okay, outside of that confidence interval. Does that make sense how I stated that? Anybody still a little? Okay, so that's what, think of it as a student. If you knew, if I said to you, would you like to earn a 95% on the next test? If you earn 95%, are you going to be like, gosh, what 5% did I not get? Or are you going to be like, dude, I got 95%, sweet, and you move on? Most of you are going to do 95% sweet, let's move on. And, look at my grade and I love life. So that's like saying, if I were to give you a test over and over and over again, and you're going to get 95%. So you're 95. So now I'm going to say, as a person, I'm not going to give you 100% sure that something's going to take place. So with this, I'm going to say, I'm 95% sure that, or 95% confident is the term they use, that my information, if I redid collecting the data of the speeds over the damn road, like, it didn't give us a whole lot of information when it was done, how it was done, but we have to assume that it was a random sample. Like they had a random number generator saying, okay, you need to count the 40th car, the 70th car, 82nd car, the second car, the 30th. If you had a random number generator, count the cars, and you collected 32 pieces of data on the damn road on a day that is right around 70 degrees, and it was a work day, so let's say it was a Monday, if we were to do the same test again, I am 95% confident that I would generate a whole nother field of 32 scores. So my grid of 32 scores, let's pretend I can draw really well. If I were to do that same data collection by doing a random sample of 32 cars during the same time, on the same day, same time of day, things like that, my new average of my new collected data, I'm 95% sure that my new mean will fall within that. So this, when I collect again, will fall within that. Okay? Yeah? Okay. Absolutely. So this is going to use your degrees of freedom. And we got that because it's one less than our amount of data. Okay? We are going to use the 95% confidence interval. Okay? Which means I'm searching for that because we're looking for one of the tails. Okay? And then, flip back to the table. So, degrees of freedom is the left column on table D in the back. It's the second to the last table. So you see where it says DF? So degrees of freedom, we're trying to get it to be 31. Unfortunately, our table goes 30, then 40. So we're going to check the 30. So we need to use this because that's the next closest to it. And so I'm down at 30. And then I'm going to go over and I'm going to find the 0.025 because that's the amount of area that's at to the tail to the far left of the 95. 95% of my data will fall within here. I'm looking for a little piece of data out here. And that's what I use. I go to 30, go to 0.025, and I find 2.042. And so that's my z-score, but I'm making it a t-score because there are certain parameters that are taking place that we're using degrees of freedom. Okay? Perfect. All right. Can I move to the last problem? Talk to me.
So, abstract question, but you have 95% confidence, correct? And then you got, for being 95% confident, you can narrow it down between 43 and 47. Shouldn't your 43 and 47 be more spread out? You're so confident, right? Shouldn't your expectation be more broad?
It's a great question. I like it. Okay. You're right in saying that, but what you're using is the new t value or the e value you found, which comes to 1.96. So because of what our original standard deviation is, our standard deviation is only, it's just under 6. It's between 5.4 standard deviation with 32 pieces of data. So this is already a pretty wide spectrum on the standard deviation. So we are 95% confident that if I were to collect 32 more pieces of data of these cars coming over the damn road, and I'm not changing anything, other than it might be a week or two later, but as long as the temperature's the same, as long as I'm using a random number generator to generate which cars, okay? And a random, we're starting to go purple again. So a random number generator is this simple. I know you know what it is. It does take place on your calculator.
So we're more narrowing an already existing spectrum. Right?
So let's see, it's under math, I think. Math, probability. Yep, rand. So if I type that and hit that, that's a random number. I hit it again, that's a random number. Okay? But now you could limit this, you could change, I don't want it to take it out that many decimals. I could go and I could change under my, yeah, no, but there's random number generators that you can use like for single digits, double digits, triple digits. So what I think you could do in this scenario for a true number generator is like, let's do an observation first and say, okay, on this kind of day, there was about 7,000 cars that drove over the damn bridge that headed west. Okay? I'm just picking an arbitrary value. So now you're going to say, okay, we want to do a test. It seems like a lot of people are speeding on this road. So let's make a test come in place that's going to take place. Now, it doesn't mean that people aren't speeding or are speeding. I mean, you might have that one guy that's doing a 110 miles an hour on the damn road going, he's a village idiot. But then everyone else might be falling right around the same range of data. So you do have that one outlier, and that's something that later you can start looking at going, okay, I did take this group of data. Boy, I have this outlier right here that it's crazy. Why would somebody be doing that fast on there? Is that really possible? Sure it is. But most of the population is going to fall within this range. So if I were to reduplicate my test, I will be 95% confident that my results will fall within those two numbers. My new mean will fall between those two numbers. That's all you're doing. And then if you go to a 99% confident, that's going to become a lot more wider. If it was 80%, it's going to be real narrow. If I said 10%, it's a slip, like a slice of a bread loaf. Yeah. All right. Being we're coming up on prom season, I think we can deal with this problem. How much do those flowers for prom cost? Uh-oh. Okay, a random sample of florists gave the following information, assuming costs are normal, constructing 90% confidence interval for the average cost of flowers for prom. It's going to be done the same way. Will you tolerate me still plugging in data?
No, we hate you.
Okay. Edit. Clear. Down. All right. Read across. 15, 12. Uh-oh. 16, 8, 7.5. 12, 16, 12, 13, 14, 8.5, 12, 15, 13, 10, 12, 7, 19, 22, 15, 35, done here. So I'm going to go stat, calculate my one variable statistics, list 1, Okay, so I have 15.64 that I'm going to use. So my mean. And my standard deviation I want to use is going to be this one right here, 7.18. Okay? How many shops are we looking at? How much? Didn't hear you, I'm sorry. 25. So we're looking at 25 shops. What's my degrees of freedom? 24. Okay? The nice thing is degrees of freedom is always one less than what your sample was. Okay? It's not going to change because based on you have more or less samples. A 90% means that you have 10% of your data that falls to your wings, which means that each wing is 5%, 5%. And 5%, 5% is the same thing as 0.05. Agreed? Okay. Table in the back of the book. Still with me? Look for our t-score. So I have a degree of freedom of 24. Does 24 exist on our degrees of freedom? And then I'm looking over to 0.05. What do you got? 1.711. Good. So I'm going to get the 1.711. Okay? Remember, I'm using this equation. So I'm going to use E is equal to T. T had been Z times standard deviation over sample. So I'm going to plug 1.711 in there. I got that from my table. My standard deviation is 7.18. My sample size is going to be 25 shops. God bless you. Someone do the math? 1.711 times 7.18 divided by 25. 2.45?
Well, technically 2.46 because it's round.
2.46?
Yeah.
Okay. So now, I'm going to use that with my mean. So I'm going to go 15.95 minus 2.46 and 15.95 plus 2.46. I'm sorry, what? Oh my gosh. Where did I get that from? I'm so sorry. Oh, jeez. You guys. 6464. Sorry about this. It's the only place it's going to affect the problem. Okay. 15, is that right now? So 15.64 minus 2.4? Yes. Yes. You got one? No. 13 point what? I'm sorry? 1.8 and 18 what? 0.10. Okay. So now, I am 90% confident that if I randomly selected these floral shops using the same type of random number generator in the same sorts of locations, that my average of my next set of data would fall between 13.18 and 18.10. So you're 90% confident it's going to happen there. Yes. That's when you are going to start using T. It had been Z. This was Z originally, which meant that they gave you a Z-score that you could find. Okay, remember Z-score theoretically could be observed minus the average over the standard deviation. And then we changed it a little bit to, some of the more problems, but it's easier to find. So it's the same idea. It's just you're using this a little bit when you don't have as much data in order to make an inference on. If you look at the bottom of that table, I think it goes up to 1,000 or something, or 100, or oh yeah. So that table goes to 1,000. Then right after that, it becomes Z. You see that on your table in the back? So that means that obviously the Z score after you get over 1,000 could continue. I mean, actually, after you get to, after 30, it's up to you if you're going to use this table. I would then, if you have more than 30 pieces of data, I would use Z rather than that. And you can actually use Z right here because the Z down here does take place. You're like, okay, I'm not worried about how many degrees of freedom I am, so I'm just going to use my Z score at the very bottom, and then your confidence interval could take place very easy. That's the bottom row before it gets to 50%, 60%, 70%. Does that make sense? Okay, so 90% of the area under the curve falls here. 5% would be here, and 5% would be here, because it has to be symmetric about itself. Okay, this coming out to you is a review, 7172. I think we could do this right tomorrow. Work on this now. What I will do is I will have a few of these with all the answers posted around the room tomorrow. So when you come in tomorrow, just go up to it. Just double check your work. I'll check this off for points tomorrow too. And then if there's any questions off this, we can go over that. And then I want to start a quiz tomorrow. If we get done with it, great. If not, we'll make it work. I could probably give you more time on Monday without having you guys come in. Let me hit pause.